that, we can actually start applying the concept of force, the concept of the first law and second law, all right? And the third law always shows up in different applications. So that's the key. So we can apply Newton's laws in different situations. So if we have a situation of equilibrium, we talk about that last class when we did the exercise on the spring, right? So let's say I give you, so you have a roof, and then you have two cables, and they are holding a mass. That could be a question I can ask on a test or even a quiz. The only thing I will ask you for now will be to do the forces diagram on that situation there. What you will need to do, what you will need to know as well is that the angles here, say this is 37, and this could be 45. All right. So to do a problem like that, you will need to first study what's going on that body. Normally, you will remove that body, and then you will start drawing the forces acting on it. You can start on the picture, and then we can move it to another, right? So, first of all, always the force of gravity, mass times gravity because of, right? Then you will have the tensions. So you have tension 1, tension 2. I'm sure they are different because the angles are different. If the angles were the same, then the tensions would be the same. But because the angles are different, then you put this T1, T2. Tension is a force that you normally experience when you pull something with a rope, string. So as you can see there, right? Let me see if I can do something about that. That's better. Much better there. Okay, so as you can see there in the screen, T1 and T2 are different, and you can actually already see the free forces acting on the body. Now, the key word is that they are in equilibrium. So what you will need to write here, remember that force is a vector. So you will have here that T1 plus T2 plus mg, and you can even put vector, vector, vector is equal to 0. That's because they are in equilibrium. When they're in equilibrium, the net force is equal to 0 newtons. So here, 0 newtons, 0 newtons. So that's a good way to start. All right? Now, of course, when we did vectors, right, I did show you how you could solve a problem like that if you were given the value of the mass, right? So just very quickly here, so you can see what I mean by that is you will bring this body here on the x and y coordinates there, and then you will put tension 1, tension 2, and mass times gravity there. What's interesting is that this angle is 45 and this is 37. How? Because of parallel lines. Alternate interiors in geometry, right? This angle is this angle there, this angle is this angle here. Okay? So that's about it. We did problems like that. Remember in the first week or second week, you will break into components. But I'm not gonna ask you for now to do that, okay? Just for you guys to know. And then you can find both tensions if you do it like that. Okay? That's a good way. So it's a very nice example to show you forces diagram, equilibrium, and how we use Newton's laws, because that one that we use there is the first law. The body will remain in equilibrium, unless the next force, unless for example I push it, right? Then the object will start to accelerate. That's the one there. Let's do another problem that is a bit more interesting. We can start doing it with equilibrium, and then we can try and do it with acceleration. I'm talking about inclined planes. So this is a situation 1. The next situation, I'm going to do it there, right, will be a situation with inclined planes. And inclined planes is another common situation in physics. Right? So that's that. Inclined planes. So let's start with equilibrium in inclined planes. For an inclined plane, you will have there, you have a mass, m, and then I have an angle here, theta. There. How can it be in equilibrium if there's an angle, if it's an inclination there? Because we're going to now add friction. All right? So let's suppose here there is a mu. That mu that you see there, that is a coefficient of friction. And we're going to put here mu s. There is a question in the homework that asks you how many types of friction there are. 2, kinetic and static. So that is static friction there. So what's making the object fall, or at least trying to fall? You will say, well, this guy, mg. But mg is pointing downwards. What about along the plane? What you will do is this very nice thing. You will draw this line perpendicular, all right? The mg is also perpendicular, and by doing simple geometry, you will find that this angle is also theta. So that is vectors upside down, all right? If this angle is theta, what you need to remember is that we can find a component that makes the object fall. This component is mg sine of theta. And then we can also find this one here. Action, reaction, right? Action, reaction. We have an action here. We have a reaction. We call that the normal force. That's the normal there. If we have that, then we know that the force of friction is the normal times mu s. So the friction is always acting opposite to the body. That's the friction there. Fs, static friction. So then you just will do mg sine theta equals to the normal times mu. But that normal there is a way to find it. Mg sine, here will be mg cosine theta. because of the way you break it into components. So I know that the normal is mg cosine theta. So you will write here mg cosine theta times mu. Look what happens, right? Mass cancels, gravity cancels, and then you get a nice result. Tangent of theta equals to mu. Right? Again, you won't be tested that on Tuesday, sorry, but I think it's a good idea to do this so it can help you to understand a little bit of the applications. I'm applying there Newton's first law and also third law, right? The action equals to the reaction. That's called the normal. And remember that the normal is perpendicular to the surface, all right? And we get friction by multiplying the normal times that coefficient, right? That coefficient is a constant depending on the surface, and it doesn't have any units. Okay, so it looks okay there, the equilibrium and the inclined planes. Let's do a problem now, now with numbers, using a little bit of friction, but now with an object that is moving. All right, we didn't do that last class, so let's see an object that is moving under a force and when there is also friction. Okay, so you can see how we use them, and that will be an application of Newton's second law. All right, so this was the first and third law. No acceleration. The net force acting on both cases was 0. So the object was there, static, not moving. All right. So let's see. Now let's do a problem with numbers. So Newton's second law. There you are. So pretty much we're gonna have a body in a horizontal table which is 10 kilograms of mass. The body is being pulled with a force of 150 newtons. The problem is asking you find the acceleration of this body if there is friction with mu kinetic equals to 0.2. So the coefficient of kinetic friction is 0.2. So that could be actually a problem that you could get in a test. So let's see how will you address it. All right. If there was no friction, force divided by mass will give you the acceleration, so 15 meters per second squared. But because there is friction, it should be less. Let's see how much less. So remember, the net force is equal to mass times acceleration. What's the net force acting on this body? So we need to, well, we have a force there, we need to draw them, like we did there, we need to draw them, but this one is easier because it's in a horizontal table. So the only thing you have to do is mg. Now gravity is how much? 9.8 meters per second square. So this is mg. 10 times 9.8, 98 newtons. But we also know there is a normal by Newton's third law, action, reaction. And because there is a normal and there is mu, we know as well, we also know that the kinetic friction equals to the normal times mu. Now, what's the value of that normal? When the body is on a horizontal table, whatever the weight is, if there's no other forces pushing it towards it, because you can have a situation where, like, for example, this chair, right? The normal of the chair will be just the weight of the chair. But if I press it, the normal will be bigger. Because on top of the weight, I'm pressing it, right? But in this case, there's not that. So just the normal equals to 98. So in that equation there, 98 times 0.2, that will give you the value of the friction, the kinetic friction. So my kinetic friction will be 98 times 0.2. That will give you 19.6 newtons. Now let's find the net force. Because remember, friction acts in this direction here. That will be the friction equals to 19.6. So what's the net force? To the right, 150. To the left, 19.6. So my net force will be 150 minus 19.6 equals to what? The mass of the body times acceleration. See? That should be how much? 130.4 equals to 10.8. So then the acceleration will be 13.04 meters per second squared. So less. As you expect, with friction, there is less acceleration, right? So that problem there is actually a good example, all right? The other ones were more to visualize Newton's laws, but this one here is a nice application, all right? We can probably do another one. I'm thinking we did Hooke's law, we sort of is centripetal force, it's just application. This one I like it because it includes a friction. We did the airplane problem using kinematics, all right? And then, well, the concepts of Newton's laws. So let me just start sharing here. There. What do we have there? We have a nice diagram, flux diagram, that shows you the changes in motion caused by forces which come in pairs, right? So if they come in pairs, according to Newton's third law, action equals to an opposite reaction, right? So for example, if you are pressing the table, you will also feel a force on your hands. That's the reaction of the table against your hands. All right? So if you push on the wall pushes on you. All right? That's if they come in pairs. If they are caused by forces, according to Newton's first law, you can be in equilibrium, or if there is a net force, then you can have a non-zero here. And then you have an acceleration. If they equal to 0, you will have no acceleration. So there can be either no change in velocity or just the body is just standing still, so not moving. Okay? Acceleration implies a change in velocity. And Newton's second law, as you have it there, force equals to ma. All right? So this is a nice diagram there, all right, to summarize what we've been doing. So we sort of did that. Okay, so at this moment, you are exerting a force that should be downward, all right? That should be downward. At this moment, you're exerting a force downward on Earth. Is that true or false? Anybody? At this moment, yes, you are exerting a force downward, all right? And then by action reaction, the Earth is exerting a force towards you, the ground, okay? In the process of throwing a ball forward, the ball exerts a rearward force on your hand, a forward force on your hand, a rearward force on the ball. The hand exerts a rearward force on the ball. The only force present is your force on the ball. So what would you guys say? 1, 2, 3, or 4? What was that?
1.
1, exactly. As you throw the ball exerts a force on you in the opposite direction. All right. The way you can also see this is like nobody has seen that here probably, but when back in the 1700s, when they were using those cannonballs, they will shoot, right, the ball with a very high speed. By action reaction, the cannon will recoil. Or the best example is if you ever go to a shooting range, right? If you shoot, you recoil, your hand recoils. That's action reaction there. Later on, we're going to talk about conservation laws, and there's something called conservation of momentum, but it also gets applied in here, in the action reaction of forces. All right? At one moment in a football game, player A exerts a force of 200 newtons to the east on player B. The size of the force that B exerts on A is what? And the direction is to the
West.
west. And what's the value of the force? 200, right? So, actually, can I use this? So, okay. So there was a way to write in there. Anyway, that's fine. So 200 newtons to the west. True or false? When you jump upward, the floor exerts a force on you that makes you accelerate. When you jump upward, the floor, the ground, the earth, exerts a force that makes you accelerate. That is true. All right? When objects fall, because when you jump, maybe you don't feel it, but then you will be accelerating towards the ground. And what did we learn last class? Accelerate with the value of gravity. Regardless of your mass, anybody, any piece of matter on Earth, when they fall, they accelerate with the acceleration of gravity. What changes is how they accelerate. Because, for example, we cannot say that a feather and a piece of iron, a hammer, will fall onto the floor at the same rate, at the same time. It doesn't happen, unfortunately, because of air friction. All right? But we know in the moon that actually is true. All right? Okay. So we've talked about these examples.